Good morning, students! How is everybody doing today? I hope you guys are doing well. So, I made a mistake yesterday. The office hours that I had intended to hold on the 1MD3 Teams page, I accidentally held on this class's Teams page, so I guess the office hours for this week were yesterday, and the office hours for 1MD3 are going to be today, because, you know, technology hates me. Doop doop doop. Cool, cool, cool. Lots of people. Lots of people. Excellent. So, yeah. Might as well get right straight into the lecture material for today. Unless there are any objections, I would appreciate somebody saying something in the chat just to make sure that it's working. But aside from that, I think we'll be doing okay. Doop doop doop. Currently is there. That's the current one. Like and subscribe. Like and subscribe. Apparently at 400 subscribers I get to monetize my channel, which means I get to have ads and get paid twice for the same job, so that would be awesome. But, you know, not really. Anywho, so, lovely. We were talking about BubbleSort. We got a lot of slides to get through. I'm not sure we're going to get through all of these slides today, but we might. We'll just have to see. 50 minutes isn't as long as you think it is, but it's even shorter when, you know, the professor is pontificating about pointless nonsense instead of actually talking about the stuff. Okay, so we were talking about sorting algorithms. Now that we've talked about arrays, how tricky they are, and all of the rest of it, it behooves us to now cover a little bit of material related to algorithms and algorithm design. Got lots of... So, I got a question about the exam. So it's December 22nd, 9 a.m. to December 23rd, 9 a.m. Yeah, so it starts 9 a.m. the day it's scheduled and ends 9 a.m. the next day. That is awfully close to Christmas, but, you know, I guess that gives you plenty of time to study. Good Lord. Anthony says, wait, do profs get paid per class taught? No. Am I clipping a lot? Am I clipping? Clip. I am clipping a lot. Maybe I just need to move the microphone further away from my face. How about that? No, that's still clipping. Testing. 1, 2, 3. Is this better for you? 1, 2, 3. Do I get excited? And am I clipping when I'm excited? No, I'm not clipping when I'm excited. Well, I might be. It looks like I'm clipping anyway. Alright. Well, hopefully that's a little better anyway. Hopefully that's a little better. And Anthony inquires into the manner in which professors get paid. We do not get paid per class taught. I am a sessional professor. That means I'm technically a part-time professor. It's quieter, but is the clipping problem. I know it's quieter. I turned it down. The thing about clipping is if you turn the volume down, that sometimes fixes the clipping, but okay. Alright. Well, maybe I'll turn it a little bit back up then. Test, test, test. Test, test, test. Test that clipping. Test that clipping. Gonna start thinking this is HQ. Anyway. Yeah, so I'm a sessional professor, which means I get a flat contract fee for each class that I teach. By which I mean each course that I teach. Sorry, not every individual class like this one. Yeah, I actually only get $8,000 to teach this, which is just a couple of $1,000 more than a TA gets to be a TA. So have sympathy for your sessionals in the upcoming, actually currently ongoing contract negotiations that CUPE is undergoing, because we're not paid especially well. God, I hope there isn't a strike this semester. Anyway, we were talking about sorting algorithms. Sorting algorithms are kind of like, when you start the study of, a more formal study of algorithms, sorting algorithms are often the one that you start with because, A, the data structure that you're operating on is about the simplest data structure that exists in a computer that isn't just an integer. Technically, a single integer is still a data structure, but, it's all data and no structure, shall we say. Arrays being, linear arrangements of memory, there's stuff that we can do with them now. So, a sorting algorithm, just to recap, takes the elements of an array that might be out of order and puts them in order so that we're going to see, when we get into search algorithms, we're going to see why it is that you may wish to keep your data sorted. It's actually quite cool. But this is, you gotta flex your nerd cred here. In order to really appreciate algorithm design, you have to be of the mind, I want all of my stuff optimized. I want my programs to run as quickly and efficiently as possible. That's sort of the mindset that you need. So we talked about BubbleSort. BubbleSort is the simplest, well, one of the simplest sorting algorithms. It's also not particularly good, but most people can remember it, and that's why it gets used. It's actually terrible compared to a lot of sorting algorithms, but essentially what it does is it goes through the entire array, checking each consecutive pair of numbers, and if those numbers are not in the correct order, it flips them, and if they are in the correct order, it leaves them alone. It traces through the list once for each element in the array, essentially, although the number of iterations you need per loop, it's a nested loop, right? The inner loop is doing these sequential comparisons, and the outer loop is keeping track, essentially, of how many of the elements in the array you can consider sorted. So, the whole business of algorithms revolves around being able to claim things about the data. So, the whole purpose of BubbleSort, or any sorting algorithm, is to be able to say about data, this data is now sorted. Sorted data has certain properties that can be advantageous to other programs. So you have to sort of imagine in your mind, like, we have data and now we are attempting to associate mathematical properties with that data. we're not just talking about ones and zeros anymore. We're talking about interpretations of those ones and zeros. I have a question. Yeah, we don't get hardly any money at all. Especially considering most of us are also still paying tuition. You know, which takes a sizable chunk out of it right there as well. But anyway, so I'm just going to recap this stuff because it's important context for the next few ones that we're going to do. That's why I'm going over BubbleSort again in this type of depth. So the number of swapping operations that were required to order this data was 13. In addition to those 13, there were 7 examinations that were made. Wait, looks like 8. It might be an error. 1, 2, 3, 4, 5, 6, 7, 8. Actually, that's 8. Pardon me. That should say 8. The number of examinations that are made that did not lead to swapping were 8. And so the next sorting algorithm we're going to look at, which is Insertion Sort, is an attempt to reduce the number of examinations that are required when the data doesn't need to be swapped. But because BubbleSort is such a basic... I was about to say a word. You can imagine the word I was about to say. Because BubbleSort is so basic, the existing state of the data has no effect on its runtime. Because it starts off assuming nothing. It establishes no degree of sortedness. Like, it doesn't look at the data beforehand to see how sorted it is and therefore how much sorting it needs. All it does is it just goes at it and sorts it. And because of that, the runtime of BubbleSort is independent of the sortedness of the array. So sortedness is a thing that we're going to... Again, this is sort of leading into Insertion Sort. But this idea that the number of swap operations, like, that's in some sense irreducible. But anyway, we're going to get there. The important thing is that with BubbleSort, our best case runtime and our worst case runtime are the same runtime. So, let's talk about big O notation. This is going to be a little bit abstract, a little bit mathematical, but it's actually not too bad when you understand big O. It's mostly just a manner of classifying the performance characteristics of algorithms. So, the mathematical analysis of the performance characteristics of algorithms is an entire subdiscipline of research within software engineering and computer science. It is actually quite difficult to measure software runtime in an objective manner. For one thing, different computers will have different runtimes. The same computer with different operating systems will have different runtimes. And something like a comprehensive survey of all computer systems is impractical, to say the least. You know, there are scientific disciplines in which it's not, like, it's never easy to verify results, right, in a scientifically rigorous manner. But the idea of doing so on computers, you know, the problem is so large as to border on the ludicrous. So, generally speaking, when we perform algorithmic analysis, we tend more towards the sort of analysis from theory rather than from practical, empirical data, especially for the purposes of determining things like big O notation. So this is beginning to change, but you know, there's always empiricists who are trying to verify things empirically, and you know, empirical data is extremely powerful. In some sense, you don't know whether your theoretical stuff is actually whether it actually works or not until you have empirical results. But for this particular approach to big O notation, we're going to be talking about a theoretical approach. The algorithms community has made some decisions about what is important and what is unimportant with respect to measuring algorithmic efficiency. Generally speaking, the time it takes a system to execute an instruction is unimportant compared to how quickly the runtime grows with respect to the input, with respect to the size of the input. So we have to think about what we mean by the size of the input. In some cases, this is fairly straightforward. When we are talking about sorting arrays, for instance, it's fairly straightforward. The size of the input is the size of the array. However, if you think back to our recursive factorial example, in that particular case, the runtime of that algorithm grows with respect to the actual size of the number itself, like the magnitude of the value of the number that you were trying to compute the factorial of. So input might mean different things in different contexts, but generally speaking, a decent approximation is the number of bits in, yeah, that's it, the number of bits into the algorithm, or at least it's proportional to that. Maybe more accurately, the number of words in. So, I have this horrible habit of jumping ahead of my slides. I even made these slides, so I have no excuse. So anyway, so what is meant by the size of the input? Generally, this refers to the size of the data structure the algorithm is applied to. In the case of BubbleSort, the size of the input is the number of items that are in the array to be sorted. In general, the relation of the input to the runtime can be expressed by a mathematical equation. Consider the following equation. R is equal to an squared plus bn plus c. Those of you who know a little bit of math should recognize this as your fairly bog standard quadratic equation. So, you know, you could solve it using quadratic formula, etc. For the purposes of classifying algorithms, we are only concerned with the largest term in the expression. Now, this is an interesting thing, because this is where the approximations start happening. Generally speaking, n is the number of operations that you have to perform, and A, B, or C is the amount of time it takes to execute one of those operations. So, you know, there may be some overhead that is unavoidable. That would be your constant C. B and A might even be the same number, but generally speaking, this is number of operations. This is time it takes to execute operations. And this is, you know, sort of in vague terms, but you'll get a better introduction to big O notation in the algorithms course that you guys are going to be taking next semester. This is kind of to introduce you to the type of parlance that you'll have to work with when you're talking about things in that course. It will be useful for you to not be hearing about big O for the first time in that course, so that's why we're doing this now. So the reason we're only really concerned about the largest term here is that think about taking the limit as n approaches infinity, right? Or, you know, think about that like large n's. As n grows, the greatest contribution that will be made to R, which is the runtime, will be coming from the highest term of n, right? So, the larger that n gets, the more the largest term will dominate. So, generally speaking, the largest term is what we're most concerned with. In terms of finding efficiencies, if we can bring down the power of the largest term, that drastically increases our efficiency, even at relatively low numbers of inputs, like 1,000. So, yes, for large values of n, the runtime will be mostly, even overwhelmingly, determined by the term with the highest power of n. We also don't care about the constants a, b, and c. Yeah, I can... Give me... Sorry, I'm jumping around here, but I just want to demonstrate something. So, in the previous, if we've got a times n squared plus b, this is something I'd do on a chalkboard, plus c, let's say n is equal to 1,000, right? N squared would be 1 million plus 1, assuming all the constants are 1, right? So you can see how the largest term overwhelmingly dictates the runtime of the algorithm, even for something like n is equal to 1,000. Imagine, n was equal to 1 million. You can see how that mathematical relationship, the n squared term, would dominate. So we also don't care about the constants a, b, and c. This is where the individual differences between computer systems will show up. If two computer systems are running the same program, the number of operations they go through will be the same, but the amount of time that those operations take will be system dependent. So A, B, and C will be system dependent. Since they're system dependent, they don't necessarily have anything to do with the design of the algorithm. This is not universally the case. Actually, a fair amount of algorithms research has gone into reducing the size of the constants because they do have an effect. But generally speaking, speaking in most general terms, we're mostly concerned about the largest power of n. The constants are also affected by the specifics of algorithm implementation. Yeah, sure. Reducing these constant terms is an active and important area of research. So to apply all of this to BubbleSort, the power of n is how many times you have to examine or swap numbers. Well, it's the number of examinations you have to make. Whether that examination results in a swap or not is kind of, incidental. The constant term is how long it takes you to do the examination or the swap. So, yeah. So in this case, when I say that for every additional element that you put in the array, BubbleSort has to make n-1 additional passes, this means that BubbleSort is proportional to the square of the number of elements in the array. The execution is. And you can see that because, we've chopped off this bit here, but you can see how it's like a square relationship, right? But anyway. So, an algorithm's runtime equation is abbreviated into big O notation. That's the big takeaway here, is that big O notation is an abbreviation of a mathematical formula. So if we have the equation an squared plus bn plus c, that gets abbreviated into big O of n squared. We will often, I'll just read the slide. We often refer to this as the complexity of the algorithm. Complexity can be different in the best, worst, and average cases, and the differences can be significant, as we're going to see with insertion sort. And we can often tell what the complexity is by looking at the algorithm. That is to say, we can derive the complexity of the algorithm analytically by examining the source code. So here are a couple of rules of thumb. Algorithms, looping algorithms, algorithms that contain loops, are big O of n to the power of k, where k is the number of nested loops. So in order to implement BubbleSort, you need 2 nested loops, so that's why BubbleSort is big O n squared. Recursive algorithms, which reduce the size of the input by half every step, are generally speaking big O log base 2 of n. And thinking about those, you can, you can see that some functions increase very rapidly with respect to the number of. Pardon me. Let me try again. There can be big differences in the amount of runtime that's generated with even relatively small values of n, right? So if you, for example, have O of n, which is linear time, that's, well, it's linear. You get 1 unit of runtime for every unit of input that you throw in there. Big O of log n, obviously a logarithm sort of goes up like that, kind of like a square root. N squared, that goes up pretty fast compared to those two, but not very fast at all if you compare it to 2 to the power of n, or n factorial, which, generally speaking, if you're talking about runtimes in those ranges, you are now in the territory of algorithms that are NP hard. This is not a topic that exists in the slides, but algorithms are generally classified on how difficult they are for a computer to solve. And if you have, you have P algorithms, which mean polynomial algorithms, problems for which polynomial time solutions exist. And then you have NP, which is non-polynomial. Generally speaking, when we're talking about non-polynomial, we're talking about 2 to the n or n factorial. These guys are very difficult problems. You're gonna talk about them in your algorithms course, but essentially the El Dorado of algorithms research, or even computer science research in general, the Holy Grail, the MacGuffin of extraordinary and impossible value, is a solution to the problem of P equals NP. If a solution to P equals NP was found, all of these exceptionally difficult problems would suddenly become super easy, and, computers would leap forward into the future by 100,000 years. It would be extraordinary. Of course, it would probably also break all existing encryption, so, there you go. But it's sort of, at this point, generally accepted as a mythical thing that doesn't necessarily really exist. I'm getting people for the other class want to join. Anyway, so all that you really have to know about big O notation is that this is how we classify algorithms according to their big O runtime complexity. And we're gonna talk more about that as we examine some more algorithms. Again, BubbleSort is big O n squared. So, let's talk about Insertion Sort. BubbleSort works. It can certainly be said to work. However, it contains redundant examinations. Insertion Sort minimizes the number of examinations that do not lead to a swapping operation. So the whole point of insertion sort is to do less unnecessary work. Insertion sort only makes one pass of the array, and it sorts it as it goes. Essentially, where BubbleSort was accumulating correct values in the back of the array, Insertion Sort is accumulating correct values in the front of the array and sorting as it goes inside of that sorted section. The overall algorithm is to examine each element in the array, passing that element back through the sorted section of the array until the correct spot is found for it. So, here's the pass-back procedure. I'll show you. Actually, I'll show you the visualization first. Then we'll go back to the pass-back procedure. So, in insertion sort, the first thing you do is you examine the first pair. If they're in the wrong order, you swap them. If not, just leave them. At any rate, in the next iteration, the first two elements of the array are considered sorted. You then examine the element that's next. Let me blow this up for you guys. There. I apologize for the coloration scheme here. I was kind of at a loss as to how to represent this. Whereas in BubbleSort, the light blue indicated the currently looked at pair for comparison. In this case, the light blue boxes indicate the number being actively sorted, and the blue numbering indicates the pair that's currently being compared by the algorithm. So in this case, 9 and 4 are both active numbers and both being compared. In this case, 7 is the active number, 9 and 7 are being compared. So we compare 9 and 7. Those are in the wrong order, so we swap them. 4 and 7 are in the right order, which means we now consider 4, 7, 9 to be sorted. The next element to examine is the next element after this sorted section of the array, which is 1. We then pass back until it has found its correct place. Now we have 4 elements sorted. That's the rough procedure. So, boom, boom. Oh, I hate it when it fit page. There. So, for each element of the array, the unsorted element is compared to the largest element in the sorted array, which it will always be adjacent to. If the unsorted element is smaller than the element it has been compared to, those two elements are swapped, and the unsorted element is then compared to the next largest element in the sorted section. This proceeds until the unsorted element is greater than or equal to the element that it has been compared to. This means that it has been sorted. At this point, the size of the section of the array that we consider sorted increases by 1, and we examine the next unsorted element. So, you can see 1 is passed back until it hits the beginning of the array. We then examine 7. 7 is swapped once. It's then equal to the next element, so we just leave it. We then examine the 3, pass back, pass back, pass back, pass back. We now have 6 elements of the array which are considered sorted. 6 is passed back, 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 and the correct place is found for it, and now the entire array is sorted. So, if you'll notice, the number of black arrows are examinations that do not result in a swap operation. The number of black arrows has been reduced substantially here. We were before dealing with 8 of them, we are now dealing with 4 of them. However, if you count the number of... Oh my goodness. If you count the number of swap operations that have taken place, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, you will note that this is actually the same as BubbleSort. So the number of swap operations has not been decreased, but the number of redundant examinations has been decreased. Do I have a question? Boop. Yeah. So, with BubbleSort, the operations it takes to sort each element decreases with the size of the sorted section. So with Insertion Sort, the operations it takes to sort each element increases with the size of the sorted section. So if you'll notice, in BubbleSort, we've kind of got this general, as we go through time, the number of things we have to do decreases as the thing gets sorted. In Insertion Sort, it's the other way around. The number, roughly speaking, the number of operations per item you're sorting increases with time as the sorted section increases. You can imagine that, if this number had to be swapped all the way to the beginning, it would take this many operations to perform, right? So you could see it as, again, that sort of triangle structure, but with truncations. Yes. So Insertion Sort is an adaptive algorithm, since its runtime is dependent on the sortedness of the array. So sortedness is a concept, right? It is another one of these things about the data. We're applying mathematical interpretations to the data again. Sortedness is a measure of how far off the array is from a sorted configuration. So it's sort of like you take each element in the array, see how far away it is from its correct place in a sorted array, and then you sum all of those displacements together, and that's a measurement of the degree of disorder. Sortedness is also sometimes called degree of disorder. The number of swaps performed in either BubbleSort or Insertion Sort is a direct measure of the sortedness of an array. And with Insertion Sort, again, because we're actually concerned with, the degree to which the array is already sorted, we are able to modify our runtime based on the degree of sortedness. So, one candidate for the worst case scenario is an array in descending order. So you can imagine, now that we have a mathematical concept of disorder, we can think about what would the most disordered array look like. What is the array that requires the maximum number of swap operations? We consider this to be the worst case scenario. So if you consider this array, in BubbleSort, every examination would lead to a swap, right? Now, there's a reason I say this is a candidate for the worst case scenario, because there can be many, you'll find this in mathematics, there might be a number of configurations that are equally bad, right? And this is not guaranteed to be the uniquely worst case scenario, although it might be. Basically, you have to be careful about the claims that you make about data. This is a thing that you actually get trained in when you're it's a thing that you get trained in both implicitly and explicitly when you go into grad school, is you start to be very careful about the claims that you make. I'm not claiming that this is the worst case scenario array. However, I think it would be a good candidate for it. Anyway, for BubbleSort, every examination would lead to a swap. For Insertion Sort, we would need the same number of swaps as BubbleSort, right? Insertion Sort does the same number of swaps. So the worst case runtime for Insertion Sort is big O of n squared, which is the same as BubbleSort. In the worst case scenario, Insertion Sort has the same runtime as BubbleSort. However, let's consider the best case scenario. The least disordered array, or the best case scenario, is an array that has already been sorted. So the amount of disorder in this array would be 0 because it is sorted. Is anybody listening to me? Am I just speaking to... Yeah, I've got 50 people listening. Okay. Am I doing this through the VPN? Good lord. Well, that's an interesting experiment. Very interesting. I'm sorry about that. Normally I shut that thing off because it tends to interfere with the stream connectivity. Hopefully I didn't kill the stream. The stream seems to be okay. My goodness. Okay. Alright. Sorry about that. So, technology, am I right? So while so for the best case scenario array, which is already sorted, BubbleSort would examine every pair the way that it typically does, but no examinations would result in a swapping operation. Insertion Sort only performs one operation per element, because it checks to see if the thing is sorted before it starts performing swaps. Pardon me. So, that's a bad way to put it. So you can imagine in this scenario, if the thing was already in order, it wouldn't need to go here for a swap, it wouldn't need to go here for swaps, all of these swaps wouldn't happen. It would just trace through the array one element at a time, and ensuring that each element is in the correct place. Since every element is in the correct place, it would just move on to the next one. So, it would actually only take the amount of time it would take to trace through that array to verify that each element is in the correct order is actually the length of the array. The number of operations performed is proportional to n to the power of 1, where n is the length of the array. So this would mean that the computational complexity of insertion sort in the best case scenario is big O of n, not big O of n squared. This is a significant difference. And you can think of the average case scenario as being somewhere between O to the n, big O n squared and big O to the n. Why am I saying big O to the n? That doesn't make any sense. The worst case scenario is big O n squared, the best case is big O of n, and the average case is somewhere in the middle. So, let's see if we can do Shellsort in 8 minutes. Probably not, but we'll see. Although Insertion Sort is an improvement over BubbleSort, the number of swap operations that must be performed has not changed. This is because each swap addresses one unit of disorder. So if you think about an array as having some total amount of disorder in it, each swap in either BubbleSort or Insertion Sort can only address at maximum one placement, like it only corrects one placement, right? One or two, depending on how you count. It may be possible to increase our efficiency by performing swaps between array elements that are not adjacent. In Shellsort, we extract a subarray, sort it, and then put it back. Repeat that a bunch of times, and then we have a sorted array. That's the general procedure. We're now talking about subarray extraction. We'll have plenty of visualization, don't worry. By selecting elements that are positionally distant, we can reduce large amounts of disorder very quickly. Shellsort is often used in embedded systems applications. It's like, okay, sure. Why am I talking to you about Shellsort? Those of you who know algorithms will know that quicksort, which is another sorting algorithm, is often preferred. So the difference between Shellsort and quicksort is that quicksort is, well, first of all, it's a recursive algorithm, so it has a pretty high demand on the system stack. And Shellsort is an in-place algorithm. Just like Insertion Sort or BubbleSort, it doesn't really require very much memory to be allocated other than the array that it is trying to sort. So, like at maximum, the size of the array again. So, because of the manner in which it operates and the manner it's configured, Shellsort is actually preferred in embedded systems applications. Generally speaking, in an embedded systems application, the amount of memory that you have to work with is very small, and the call stack is, because call stack is memory, the call stack is generally pretty small as well. So recursive algorithms are not necessarily your go-to solution, shall we say, if you're programming for embedded systems, which all you mechatronics people, you should be concerned about programming on embedded systems, because that's what you're going to be required to do in third year. And all of you who are in engineering physics, who are taking this course because you wish to major in the whatever it is program. It's like smart devices or something. Basically, that's angling to you towards the Internet of Things, Internet of Things field that's opened up in recent years. And so embedded systems applications is another thing that you're going to be concerned about in the future. So yeah, Shellsort is an actual sorting algorithm that's considered efficient enough to actually be used in the wild. BubbleSort and Insertion Sort are generally speaking only used by people who can't remember or can't wrap their noodle around any other sorting algorithms and just need something to work quick. But Shellsort is like something that you would deploy in a commercial context. So it's a good algorithm. Shellsort is a good algorithm. So, in order to understand Shellsort, we need to talk about H-gaps and interleaving. So I'm going to show you the... Oh, I have some diagrams. Okay, I'm going to read this slide, then I'll show you the diagrams. The key to Shellsort is knowing how to break down the array into subarrays. Subarrays are formed by taking an element, take some element of the array, skip H elements, and then taking that next element until and you repeat that until the end of the array is reached. So it's like take one, skip some, take one, skip some, take one. The sequence of H values used varies by implementation. With sequences, different sequences have been proposed over the course of time by different researchers. It's interesting, the runtime characteristics of Shellsort are actually dependent on the sequence of H values that you use in order to sort the array. The most recent one was proposed in 2001, so quite recently, and that sequence is 1, 4, 10, 23, 57, 132, 301, 701. Of course, you start with the biggest gaps and sort down to the smallest gaps. So you would start at 701, then go to 301, etc., etc. This sequence of H-gaps was experimentally derived. We don't know what equation these guys conform to. It's possible that they conform to an equation, but that hasn't been... that's an active area of research, shall we say. So the next item in the sequence cannot yet be predicted. We would have to find the next element in the sequence experimentally, unless one of you guys is clever enough to figure out what the formula that predicts the next value is, and then publish a paper on that, and then verify that experimentally, and that would be a paper. That would actually be probably a really important paper. The worst case performance of this sequence is currently unknown. Hasn't been experimented on, but generally speaking for Shellsort algorithms, the worst case performance can be I think as low as n to the 3/4. So it's like n to the 3/4, which is pretty good. It's better than n squared for sure. So this is how you would visualize h-gaps. So imagine h is equal to 6. We take 0. We 1, 2, 3, 4, 5, 6. We take 6. 1, 2. Actually, this would be h is equal. Anyway, I think this is h equals 5, not h equals 6. Good lord. Sorry, folks. I made all of these myself, and I think I may need to correct them. Yeah, this is inconsistent with the next few slides. I'm going to fix these diagrams, and then I'll re-upload the slides. I apologize for that. This is actually h-gap of 5. But you count 5 numbers, and then you take another value, then you count 5 numbers until you hit the end of the array. Another way of visualizing this is taking the array and arranging it as a matrix, and then taking the columns. So if you take 6 elements and then you put the next 6 elements underneath them and then take the columns, then you end up with 6 sub-arrays. In this particular case, because this is an array of size, the size of the array doesn't actually matter. So you can see these are the sub-arrays that we get. If we were to use h is equal to 3, not 4, it would be a similar procedure. You'd just, pop 2 on the bottom, so you'd end up with 3 arrays of size 3. But yeah, anyway, if you guys have any questions, I will take the questions now. If you do not have any questions, I will end this stream and go get some lunch. But yeah, we'll continue this. Looks like we've got about 1 more lecture's worth of material in this topic, so we will cover that on Tuesday of next week. Doop, doop, doop. Boop, boop, boop. When will the assignments usually be released? Well, we're definitely going to give you guys at least a week to work on your assignments. The next assignment will be finished within the next couple of days, so I'll be releasing it as soon as it's together. It'll be sometime in the next couple of days. Yeah. With respect to like a general pattern, believe it or not, I had intended to have the assignment out earlier this week, but the whole world blew up, so it was not as possible. Don't worry, the assignment is reasonably. It's reasonable to complete in a week. The majority of the assignment is actually just implementing these 3 sorting algorithms, so I hope you guys have been paying attention. And there's like 1 question on recursion as well, and like 2 questions as well that aren't super difficult. Yeah, anyway, hopefully that's an answer. Will you be notified when it's released on Avenue, or do you need to check JHub? I will post an announcement when it is released. I will post an announcement on Avenue. It will be released on both JHub and Avenue, as as per the usual. Cool. Well, seems like that's all the questions. So, I guess that'll be the lecture for today. Have a nice weekend, everybody. Go in math. Go in math, my children.